Hi, welcome back. In this last video on equality, for now at least, we're going to look at how we can deconstruct equalities at complex types into equalities at smaller types. So to hopefully make this a bit clearer, I've declared this syntax declaration here. So the way to read this is kind of backwards. So here is my new syntax, where I have an x and I have an a in the middle and then the y. And this should be the same thing as this thing on the left, which is defined to be just an ordinary equality, but where the a is this implicit thing. So all I'm doing is I'm making this a explicit in the middle of the thing, and I hope that's clarifying rather than confusing. So here's a typical question that we want to ask. Let's say that I have a pair of things, a, b, and another pair of things, a prime, b prime, and I would like to know that they are equal at this product type, a times b. And the claim here is that it's enough if the first components are equal and the second components are equal. So a is equal to a prime and b is equal to b prime. And then I'm claiming that I can make the whole pairs equal. So let's see if we can prove this. Okay, how do we do it? Well, we do it the way we always do it, by pattern matching on the right things. So let's pattern match on, say, the p and see what happens. Okay, we see that the only pattern that could possibly match is REFL, and something has happened. If that was REFL, that means that a must have been the same as a prime, so that a prime has now turned into an a here. Right. So let's pattern match on the q as well and see. Well, now the b turned into a b prime, or the other way around rather, so that now we are left with something trivial. We can just say REFL. Okay, so we see that in order to prove that two pairs are equal, it's enough to prove that they are component-wise equal. So if faced with this goal, then we can apply pair equals to typically two question marks, and then we have two simpler things to prove before, and then we are done. Right. Okay, so let's see if we can do the same thing, not for just products like this, but for dependent pairs. So that's a sigma type, right? So here the elements are still pairs of things, but now the type of the b depends on the first one. So I have a and a prime in a, but I have b in b of a and b prime in b of a prime, right? So if this b doesn't actually depend on a, then this is the same as the previous case, but it could also depend on it. Okay, so what should we actually ask for in order to get enough evidence that this pair is equal to this pair? Well, we should certainly, just like before, ask that the first components are equal, right? But now it's a bit trickier what to ask about the second components, because if we look at the types involved, we see that b and b prime don't have the same type, right? But we have to ask for equality at a certain type. So here I said it should be a b of a, but we could also do a prime and vice versa, right? But no matter which one I pick, only one of these will actually fit, right? So if I make it b of a, then the b will fit, but the b prime won't, etc. So I think I'll make it a b prime, a prime, just to be clear. So down here, I can certainly put in the b prime, but here I can't put in the b, right? Even though I would like to, because the types don't match. So what can I do? Well, these two types are not obviously the same, right? But I do have a proof which says that they are the same. So if I name that, calling it p, okay, then I could use that proof to substitute the b prime to make it go into the right thing, because that's exactly what subst is doing. It's saying that I have a proof that x equals y, and I have something in b of x, then I should get something in b of y. So here, if I subst in b using the proof p, then I get something which lives in the right type. So it's a little bit more complicated just to state it, but at least now we have a candidate. We still have to prove it, of course, right? Okay, so what should we do? well, let's pattern match on the P. Okay, and now something amazing happened. So first of all, the A primed turned into an A, just like before. That's very good, but not so amazing. What's really amazing is that the type of Q is now much simpler than we would expect, right? So the type of Q is this thing, which had this strange subst in it. But now, because we pattern matched on the P, and the P turned into a REFL, and by definition, subst or REFL is just the identity, that thing just disappeared. So the type of Q is now very simple, and we can pattern match on the Q as well. And if that is REFL, then we see that we have a simple goal in front of us. We can finish that. So the proof is exactly the same, but there are non-trivial things happening with the types here that you can't see after you pattern matched, but things actually work out. Okay, so we can do pairs. What about functions? So let's say that I have two functions. I made them dependent. So for every x in A, they return something in B of x. And I would like to prove that they are equal. Well, what could I possibly deconstruct this as? Well, would like to say that they are equal if they are equal at each component again, right? So for every x in A, f of x and f prime of x are the same thing at this type. So this time there's no problem with them living in different types because they always go to B of x. But if I try to prove this, then I don't actually know how to do it, right? Because this time I have this P, which itself is a function, so I can't pattern match on the P. And I don't know of any way to make progress. And in fact, there are counter models where this is not true. So this is not provable, which is a bit disappointing because it's really useful. And because it is so useful, then we're often going to assume it anyway, because there are also models where it is true. So it's an undecided principle that it's true in some models and false in some models. So what we're typically going to do is we are going to postulate this. So there's a keyword called postulate in Agda, where you can just assume that you have something of the right type, and then you can use it. So of course you can postulate things that are not true, and then you can typically prove anything. So you have to be careful when you postulate things, but if you postulate things that you know are true, then it just means that you're restricting yourself to a smaller class of models, which is not so bad. And this is such a useful principle that we're using all the time, that we're going to allow ourselves to postulate it. I should also say that in things like cubical Agda, if you know about this, this is actually provable. So there are other alternatives. But if you want to prove that two functions are equal, you need some principle like this. Okay, so we looked at some of the type formers that we have, so pairs and functions. Another one we have is equality itself, right? So we could ask the same thing here. When is it the case that two equality proofs are equal? Because this is in itself a type, so it makes sense if I have P and Q, which are proofs that x equals y, then I can ask the question if P equals Q or not, right? And the claim here is that they are always equal. So there is at most one proof that x equals y. So let's see if we can prove this. Well, how would we do it? Well, again, now we're back in the happy land where we can pattern match on things. So I can pattern match on the P. Okay, the only case is that it's a REFL. And I can pattern match on the Q. And the only case is that it's REFL, in which case it's easy to prove that REFL equals REFL. That's itself REFL. Right, so in Agda you can actually prove this principle of uniqueness of identity proofs. So it's called UIP quite often. And this is equivalently known as axiom K, which is a particularly bad name, and the reason it's named like this is because in the first version of the first papers about type theory, this equality type was called the identity type, so it was called I, and then the next letter after that was used was J for the eliminator for this type, and after J comes K. So that's why you have a completely incomprehensible name. But just like there are models where FunX is true or not true, there are also models where UIP is true or not true. And if we not insist on having UIP, then you can get new interesting models where, for example, you can have FunX, which you might not be able to have in some models with UIP. So these are not incompatible. You can have both if you want, but there are certain models where UIP is false and FunX is true, for example. And this is quite a vibrant research field called homotopy type theory. It's related to cubical algebra, which maybe we will have an opportunity to look closer at some point. So if you want to do homotopy type theory, then there is a switch which you can turn on in algebra, which is the without K switch. And if you do that, then this proof does not go through anymore. So you're restricted to not use this axiom K behind the scenes if you use the without K switch, and that means that you are compatible with homotopy type theory. Okay, but I'm going to turn that off again. So for this class, we're happy to use K most of the time. Okay.